Professor.
Hi there. How are you guys?
Doing well. How are you?
I'm hanging in there. It's definitely a Monday.
Do you have any NIH proposals going in today for the R01 deadline?
No, but I meant to. I wanted to, and it just didn't work out. So I have a resubmission that will hopefully make it in on the next cycle. But yeah, that's okay. Can't win them all.
Yeah.
Okay. Can y'all see my slides?
Yep.
Great.
Yes.
Thank you. Okay. All right. Happy Monday, everybody. You guys seem like you're in a good mood today. That's good. I hope everyone had a nice weekend. Enjoyed a little bit of sunshine this weekend, even though it was kind of chilly. So we're going to start off today stretching out our brains as usual. Kind of picking up on where we left off on Friday, where we had just talked about molecular polarity, so the overall dipoles of molecules as opposed to bonds. Well, we talked about bonds too, but so take a look at these three molecules and think about it for yourself. Which of the following molecules are polar? And someone's asked in a chat box about lecture slides from last class. They're posted now. I just made them visible within the last 15 minutes. I had a little bit of a technical difficulty with that, but they are up now. So you guys should be able to see them under the chapter 2 module because now we're on chapter 2. Okay, so back to stretching out our brains. Out of these three molecules, which ones are polar? Is it the first one? What do you guys think? Is it the first one? Is this first one over here polar?
No, I think it's the second one.
We want to see which one's polar. So in order to think about which one's polar, you want to be thinking about the dipole moment of each bond and the angles that those dipole moments are going in. And then you want to think about, if you add up all those dipole moments together, which ones are going to cancel out and which ones are going to add together to point in a particular direction. So if we draw in some of those dipoles, I'm only going to draw in the super important ones, which are the carbon-chlorine ones. Then we can see on this molecule on the left, these dipoles are both pointed towards the left, right? There's one pointed up and one pointed down, but those will cancel out in the up and down direction. And so the overall dipole of this molecule is going to go in that direction. What about this one in the middle? You have the same bond dipoles. And of course, there's other bond dipoles on the CH bonds too, but they're much smaller. Well, actually, let's go ahead and draw them in. So for the CH bond dipoles, they're going this way because carbon is more electronegative than hydrogen, but they're very small. And so what about this middle one? Is it polar or non-polar? Anybody?
Is it non-polar?
Yeah, that's right. This one is non-polar. And that's because the dipoles cancel out because they're pointed in opposite directions, directly opposite directions. And so they'll cancel each other out. And same thing with the CH dipoles. So you can kind of see that in the symmetry of this molecule. We're not going to get into symmetry in this class. That's for a different class. But intuitively, you can kind of see that symmetry. What about this molecule down at the bottom? Again, we can draw in our major dipoles. And when we draw in our major dipoles, we see they're both pointed in a particular direction. What direction is that?
Downwards.
Downwards, right. So the overall molecular dipole for that molecule does exist. So it is a polar molecule. And that molecular dipole overall does go in kind of the downward direction. Okay. So let me see if I can get rid of all of my ink. Okay, cool. I didn't put this question up here, but take a look at these molecules and think for yourself for a minute about their isomeric relationships. So first of all, are they isomers? Do they have the same molecular formula as each other? Are they isomers?
Yes.
Yeah.
So they're all C2H2Cl2, and so they all are isomers. So what about this one on the left and the one in the middle? What's the relationship between those two? You guys know about two isomers so far. You know about constitutional isomers, where the bonding order is different and the bonding arrangement is different. And you know about geometric isomers, where the bonding arrangement is the same, but atoms are pointed in a different direction in space. So what do you think, which word applies best to these two? So I'm asking about the one on the left and the one on the right. Are they constitutional, or are they stereoisomers or geometric isomers? We got a mix of answers coming in the chat box. So let's break this down. These two are constitutional. And the reason is that the definition of constitutional isomers is that the bonding patterns are different between the two molecules. So the easiest way to think about that for me is to think about what the condensed molecular formula would be, because the condensed molecular formula doesn't give us any indication about directionality or orientation in space. But we can also look at it a different way, where we pick an atom that we seem to think is similar between the two molecules, right? So that carbon seems like it's analogous between the two molecules. And we look at what's bonded to it. So the carbon that I've circled has a chlorine, and carbon in the molecule on the left, and a hydrogen, chlorine, carbon bonding pattern in the molecule in the middle. And so right off the bat, we know that these cannot be geometric isomers because they have a different bonding pattern than geometric isomers would be. Okay, so if we think about that, and if we expand it to kind of a different version, let's look at then the middle one and the one on the right. What's the relationship between these two isomers? We can take a look at that same carbon atom, right? And now when we look at that carbon atom, the analogous carbon atom on these two molecules, we see that that carbon is bonded to a hydrogen, a chlorine, and a carbon in both cases, right? And indeed, if we go through and we do that for every atom in the molecule, we'll find that it matches up perfectly. This carbon, the double bond of the carbon at the right of the double bond, it's bonded to a hydrogen, a chlorine, and a carbon in both cases. Now, of course, they're pointing in different directions in space, some of the bonds, but the bonding pattern is the same. Does that make sense? So these are indeed geometric isomers because they have identical bonding patterns. And the only difference between these two is that in one of them, the chlorine on the right is sticking to up, and in the one on the other one, the chlorine on the right is sticking down. So they are geometric isomers. You can also call them cis-trans isomers. So which one's cis and which one's trans? How about this molecule on the right here? What's this molecule on the right? Is it cis or trans?
Trans?
Nope, this one on the right is cis, the far right. Man, it's getting really ugly. Let me clean things up here. Okay, the one on the far right is cis, and that's because what we want to do is we want to draw basically a plane through our hot dog. So we have on one side of our hot dog, we're going to have substituents, and on the other side of our hot dog, we're going to have substituents, right? And so what we're looking for is a matching pair of substituents, like the chlorines, for example. And if that matching pair is on the same side, then they're cis. And if the matching pair is on the opposite side, then they're trans. Okay, I know the slide's gotten kind of crazy, but do you guys see what I'm talking about here with the cis and the trans and the types of isomers?
Yep.
Cool. All right, let's get back to laser pointer. Okay, now that our brains are warmed up, just a couple of administrative things for you guys. I am not going to have office hours today. I am going to supplement a little bit later in the week with an additional office hours. And the reason for that is because I'm not going to release your quiz grades or answers. Well, I guess you can already see your grades, but I'm not going to release the quiz answers until Wednesday. And so because you guys might have questions about the quiz, I wanted to wait my office hours kind of later in the week. So that is what I'm going to do for office hours. On Wednesday, I will make some additional comments about the quiz. I know some of you have emailed me some concerns on different fronts, and I will address all of those concerns on Wednesday. I have posted a new Achieve homework. I told you guys last week that this is coming, and it is indeed up and open. I have it currently due Monday morning at 9 a.m. So if you are planning on watching the Super Bowl and staying up late and all that kind of good stuff, just make sure you get this done beforehand. We're going to be actually coming all the way through chapter 2, either by the end of class on Wednesday or part of class on Friday. So you guys will have plenty of time with the material to do that chapter 2 homework. And somebody has asked if the exam is still planned for Monday. And so thanks for that segue. Exam 1, I would like very much to keep to the content of exam 1 being chapters 1 through 3. And we will not make it in time for an exam on Monday, 2/14. So I am still looking at the calendar to chart out when we will make it there. It is likely that exam 1 will be next week sometime, but I will figure this out and I will make that announcement on Wednesday during class. Okay. All right. So we are going to, somebody's asked in the chat box, do the questions on Achieve go in the same order of topics you teach in class? There's no guarantee for that. So the Achieve homework is broadly based for chapter 2 or chapter 1 or whatever. You'll have one Achieve homework for every chapter that you do, every chapter that we cover. And there's no guarantee about the order of the Achieve questions matching what I do in class. Typically they tend to, but that's not a sure thing. So you should be able to tell when you look at the question and read the question whether or not it's a topic that we've covered in class. And just know that if we haven't, then we will. Okay. I'm going to address all of the exam questions when I announce when the exam will be. So save your exam questions for after I go over the format of it, which will be on Wednesday. So for today, what I'm going to do is take us through chapter 2. So we got a head start on chapter 2 on Friday, and we're going to come most of the way through chapter 2 today. I hope to get to acids and bases today. And I want to point out down here at the bottom, these last couple of topics here called organic functional groups. This is material that isn't particularly conceptually challenging. It's just it's like definitions and terminology. So I will touch on these in class on Friday, but you're going to be responsible for knowing and understanding these on your own. I'm not going to spend a whole lot of class time on it, but the functional groups are going to be things that you need to know for this chapter. Okay, so let's go ahead and get started. I'll remind you guys where we left off on Friday with just a quick refresher about polarity, and just kind of 2 slides to bring us all back to the same place. So first of all, we talked a bunch on Friday about the dipole moments of individual bonds. We talked about how we got a preview of that stuff in chapter 1, but on Friday we went into a little bit more depth and talked about how those dipole moments are mostly due to the electronegativity difference between the 2 atoms, but they also have to do with the distance apart that those 2 atoms are, so the separation of charge. And we talked about periodic trends, right? That if you are looking at trends along a row of the periodic table, then as you increase the electronegativity of the bonding partner, if all else is the same, then you're going to increase the polarity of that bond. Now, this trend works really nicely if you're looking at a row on the periodic table, but the trend gets a little bit cloudier and muckier if we try to look at a column on the periodic table. And you can see that reflected in this chart here, where if you look at carbon, nitrogen, carbon, oxygen, carbon, fluorine, it's a nice trend of increasing dipole moments. But if you try to look at the trends among the halogens as you go down the periodic table, you can't really see a clear trend among the dipole moments. And that is because the electronegativity scale, which electronegativity goes up as you go up the periodic table, the electronegativity difference between the two partners is working antagonistically, or it's working opposed to the bond length or the bond distance as it relates to bond dipole moments. Okay, so that's about particular dipole moments of bonds. And we also talked about taking that information and adding up all of the dipole moments of bonds together in a vector sum sort of a fashion, where we look at both the size of the dipole and the angle or the direction of the dipole. And by doing that, by adding all of those things up, we can get the molecular dipole moment, or a measure of the overall polarity of a molecule and the direction of that polarity. And we talked about how lone pairs are a contributing factor here. So here are some of the examples that I showed you guys on Friday. And you can see that it doesn't necessarily, just because you have polar bonds in a molecule, doesn't mean that the molecule must be polar. So in the case of ammonium, which is protonated ammonia, you have a tetrahedral configuration. That nitrogen in the middle is sp3 hybridized, and the dipole of each bond ends up canceling each other out, and you have a net overall molecular dipole of 0. So that's the example of ammonium. I also gave you guys some examples that have carbon-oxygen double bonds. Carbon-oxygen double bonds are highly polar. They're very strongly polar, pointed towards the oxygen, in part because of that electronegativity difference between carbon and oxygen, but also in part because of these lone pairs and what direction the lone pairs point. Now, in the case of formaldehyde, that lends itself to give an overall dipole of the molecule pointed to the right in the way I've drawn it here, so pointed the same direction as the carbon-oxygen double bond. But if you have something like carbon dioxide, where if you draw the Lewis structure for carbon dioxide, you find out that carbon is sp hybridized, that the carbon-oxygen bonds are exactly 180 degrees apart from each other. And so they're pointed in opposite directions, and the bond dipoles cancel each other out to give a net dipole of the overall molecule of 0. So this was, this kind of covers our summary for polarity in terms of bonds and overall molecules. And what we're going to do now is take what we've learned about that polarity and apply it to some actual physical properties. So, well, before we do that, well, we'll kind of do that now. Okay, so what we're going to do is take what we've just learned about polarity and sort of translate it into how molecules interact with each other. So to do that, we're going to cover intermolecular forces, which I think you guys may have seen or heard about at least some of these before. So for intermolecular forces, what we're talking about here is the overall molecular dipole of a molecule and how that impacts how the molecule interacts with other molecules, either of the same type or of a different type. And what we find is that this is kind of cool, I think. So we're looking at fundamental properties that we can just predict based on the structure, which we know how to draw because we know how to draw Lewis structures. And we can use these dipole moments to start to begin to predict actual physical properties of compounds. So trends in boiling point, for example, or trends in solubility. What we're going to talk about over the next couple of slides is the different types of attractive forces between molecules. And so they can call these attractive forces, but more often we're going to call them intermolecular forces. And there are 3 types. I'll give you kind of an overview of them here. And then over the next couple of slides, I'll dig into a little bit more detail on each. So the first type is called dipole-dipole forces. And that's when both of the molecules involved have a polarity to them. So they have a dipole already inherent and intrinsic within the molecule. The next one is called London dispersion forces or van der Waals forces. And these types of intermolecular forces are what is dictated when there is no overall molecular dipole in a molecule. So these are going to be non-polar molecules interacting with other non-polar molecules. And the third type of interaction, the third type of intermolecular force that we need to consider is hydrogen bonding. So hydrogen bonding is most often for organic chemistry going to be groups with molecules with OH groups or NH groups. And so there's a little cheesy acronym here. Hydrogen bonding is fun because it's mostly very electronegative elements that are participating, either fluorine, oxygen, or nitrogen, and the hydrogen atoms that are attached to those very polar and very electronegative elements. So we're going to go into each of these three in a little bit more detail over the next couple of slides. First, we're going to start with dipole-dipole interactions. So again, remember I said these are molecules that have an inherent or an intrinsic dipole, so molecules that are overall polar. When you have a molecule that's overall polar, that means that there's going to be kind of an edge of the molecule or a side of the molecule that's delta negative and a side that's delta positive. And now remember, way back in the beginning with you guys on class 1 or class 2, I talked a little bit about how chemistry is actually based on physics, right? The chemistry is no exception to the laws and the rules of the universe. So we can apply concepts of physics when we're looking at these molecules. So if every molecule that I'm showing you here, these are chloromethane, they're polar molecules that point with an overall molecular dipole pointing to the right, as I've drawn them on the slide. And there's a negative charge buildup on the right side of each molecule and a positive charge buildup on the left side of each molecule because of this highly polarized carbon-chlorine bond. So what happens when you put a bunch of these molecules together in a bucket is that they kind of organize themselves for the most part like this, so that you have opposite charges attracting each other, and the negative end of one will bump up to the positive end of another, and it'll just kind of keep going on like this. So these are what's called dipole-dipole interactions, and that's going to be what happens when you have two polar molecules that are interacting with each other. Now, I want you to think about this for a minute. So I've told you these are organizing themselves, and that they're doing it because they have some attraction between a delta negative and a delta positive. What do you think that means for how easy it is to take them apart? Well, they have this attractive force between them. So that means that you have to put in some extra energy to separate the molecules from each other and overcome that attraction. And so what that means is that these dipole-dipole interactions, or molecules with dipole-dipole interactions, end up having boiling points that are a little bit higher because of needing to overcome that attraction. So I just want to point out there are no hydrogen bonds on this slide at all. Hydrogen bonding is the strongest one. So someone's asked in the chat box, hydrogen bonding is the strongest one, right? And that is true. It's probably a question that popped up earlier on the last slide and I just didn't see it. But I just want to point out there's no hydrogen bonding going on this slide. These are only dipole-dipole interactions here on this slide. And we're just talking about the interactions of polar molecules interacting with polar molecules. Okay, so let's contrast that with non-polar interactions, or the London dispersion forces or van der Waals forces. So when we have a molecule that's non-polar, it's overall non-polar, and it's kind of average electron buildup or charge buildup averages out to 0. But that doesn't mean that there's not movement of the electron clouds within the molecule, and that movement of the electron clouds within the molecule can create temporary dipoles in the molecule. So even though there's not an intrinsic molecular dipole of this molecule pointed in one particular direction, and the overall average of this molecule, the molecular dipole is 0. Within the electron cloud of the molecule, there's electrons kind of shifting around a little bit and creating these temporary dipoles. Now, when you have a molecule that has these temporary dipoles and you bring it close to another molecule that doesn't have an intrinsic dipole but is more nonpolar, it can induce dipoles in its neighbors. So you can see that going on in this picture down here on the bottom, where if we, brought this kind of blue molecule over towards other blue molecules, the negative charge area on one side will induce the neighboring molecule to create a positive temporary dipole nearby to help stabilize it. So what I'm talking about here is temporary, again, dipole moments within a molecule that can then influence the neighbors of that molecule to get a temporary dipole moment. And this is going to be how nonpolar molecules interact with each other. This nonpolar interaction, which is called, again, London dispersion forces or van der Waals forces. So it turns out that this temporary dipole is more likely to happen the bigger the electron cloud is and the farther away it is from nuclei. So that concept is called polarizable. So the more polarizable a molecule is, the more likely it is to have temporary dipoles created. There's other really technical words for polarizable, like squishy, right? So the squishier an electron cloud is, the more polarizable it is, the more you can move and mesh around those electron clouds. And another way to think about this is about the surface area. So I'm going to show you a slide that demonstrates that. These three molecules here are all using, they're all pentanes, right? So are they isomers, these three molecules? What does it mean to be an isomer? Same overall molecular formula. So it turns out these three are all isomers. They all have the molecular formula C5H12, but their bonding order is different. So the arrangement of bonds within each molecule is different. So what kind of isomers are these?
Constitutional.
Nice. Yeah, these are constitutional isomers. So with these constitutional isomers, which again all have 5 carbons, you can see the one on the left, the linear N-pentane, those 5 carbons are spread out. And the one all the way on the far right, which is a very branched version called neopentane, those carbons are packed real tight. So you can imagine that the electron cloud for the overall molecule, like all of the electron clouds of the molecule combined together, they're bigger and more spread out in the spread out linear pentane than they are in the condensed branched neopentane. And so what that means is that N-pentane, the linear version, has more opportunities to create temporary dipoles and to induce temporary dipoles in other molecules that it encounters than the condensed version, which has a smaller surface area and therefore an electron cloud that is more dense and less squishy, right? So we can see that reflected in the boiling point trend for these 3 constitutional isomers, where the one on the left, the linear N-pentane, has a boiling point of 36 degrees Celsius. And as you introduce more branching and shrink the surface area because you're condensing that molecule, then you drop your boiling point down to 28 and then finally down to 10 degrees Celsius for neopentane. And it's because of this van der Waals forces being minimized the more condensed your electron cloud is. Okay, so I don't know how many of y'all actually read your textbook, but this little guy is from your textbook. And it turns out that on his fingers, this little gecko, on his fingers, he has all of these little tentacle-like things that come out, they're cilia. And on the edges, like at every little one of these things, there's a bunch of nonpolar molecules. And it is this set of nonpolar molecules that allows a gecko to stick to glass because glass itself is fairly nonpolar. And so all of these little interactions, even though they're all very, very weak, because there are so many of them, they add up to enough strength to support the weight of our friend here. So you can read more about that in your textbook. Now we're going to go on to the very last form of intermolecular forces, which is called hydrogen bonding. And you'll hear me say this super cheesy saying all the time: hydrogen bonding is fun. And the reason is because that's an acronym to remind us that it has to have a fluorine, oxygen, or nitrogen in order to participate in hydrogen bonding. Okay, so it's not just having a fluorine, oxygen, or nitrogen that enables hydrogen bonding. These molecules that can do hydrogen bonding have to have an NH or an OH bond or an FH bond, but they have to have a hydrogen atom that is part of a highly polar covalent bond, so that the hydrogen atom has a very strong delta positive to it. These molecules tend to have very strong dipoles and are very polar. So what happens in hydrogen bonding is that the hydrogen, of course, attached to a nitrogen or oxygen, the hydrogen from one molecule, because it's so delta positive, because it's attached to something that's so electronegative, that hydrogen ends up being strongly attracted to a lone pair of electrons on another molecule. And so I'll draw you out or show you guys some diagrams here that help solidify this. So on the left, we have methanol. It's the simplest alcohol. And you can see we have our oxygen of methanol with our two lone pairs, and we have an OH bond. So in the case of hydrogen bonding, the hydrogens that participate in hydrogen bonding have to be strongly polarized. They have to be very, very delta positive. So it's only these OH bonds or these NH bonds that can do this. And the delta positive H ends up creating a strong interaction with a lone pair of electrons on a neighboring atom, so on a different atom. And these hydrogen bonds are represented by these dotted lines. So the key feature here in making this happen is the polarity of that OH bond, or in the case of methylamine, the NH bond. And that polarity gives that hydrogen atom a very strong delta plus. Notice methanol still has three other hydrogens, right? And methylamine actually has, well, three here and then one there. Don't worry about that. But these CH3 hydrogens, these hydrogens that are attached to carbon, they can't participate in hydrogen bond. And the reason is because their polarity of those bonds is not very great at all, right? A CH bond is fairly nonpolar. It's considered actually just nonpolar. And so the hydrogen atom, although it has a little delta H, a little delta positive, that delta positive is too small to really create a hydrogen bonding situation. And that's reflected here in my little note to the side, that only the hydrogen atoms involved in the polar covalent bonds, so only the OHs, the NHs, the FHs, only those can participate in the hydrogen bonding activities. So someone in the chat box has asked, does this mean that the molecules that have hydrogen bonding will also have dipole-dipole forces? That's a great question, and the answer is yes. So by and large, I think that this is going to be a universal statement. If you have a molecule that's capable of doing hydrogen bonding, then that molecule also has some strong dipole on it. And so it's also able to participate in dipole-dipole forces. But the hydrogen bonding forces are so much stronger that they kind of are what's dictating the physical properties of that molecule. That makes sense? Okay, so let's see an example of this at work and try to drive this point home. So here's two molecules. Are these molecules isomers of each other? So what's an isomer? It has to have the same overall molecular formula. So are these guys isomers of each other?
I think so.
Yes, they are.
They sure are. So the molecular formula of each would be C2H6O. if you count up all the hydrogens, count up all the carbons, count up all the oxygens. So these are isomers of each other. Clearly, they're connected in a different pattern than each other. So what kind of isomers are they?
Constitutional.
Thank you. Yeah, constitutional. Okay, so these are two constitutional isomers of each other. So keep in mind now we have the same atoms, the same number of atoms of each type. We've just connected them in a different way. And check out the boiling point difference. Ethanol has a boiling point of 78 degrees. Dimethyl ether has a boiling point of negative 25 degrees, meaning not a liquid at room temperature. Okay. Sorry, not a liquid at atmospheric pressure. Wow. Okay, so for hydrogen bonding really dramatically increases the boiling point of the molecule. So if you look at these two molecules, the dimethyl ether, the molecule on the right, only has hydrogen atoms connected to carbon atoms, which means that none of the hydrogen atoms in dimethyl ether can participate in hydrogen bonding. Of course, it still has an oxygen, so it still has some lone pairs, but it cannot participate in hydrogen bonding because it doesn't have the hydrogens to support that. However, if you look at ethanol, ethanol has an oxygen with its lone pairs, so it can participate in that sense, but it also has an OH bond, which is highly polarized, which means that this hydrogen atom here on the edge of the molecule has strong delta positive and can then interact with the lone pair of oxygen on another molecule of ethanol, making a hydrogen bond. Okay, so here's another comparison for you guys. We're gonna look at ethanol, which is the same alcohol as what we looked at up here, versus ethylamine, which we have a nitrogen and NH2 group replacing the OH group. So it turns out that in this case, the OH is more polar than NH. That should make sense to you guys because oxygen is more electronegative than nitrogen. So that means that the delta positive on the hydrogen on ethanol is going to be more than the delta positive on the hydrogen that's on nitrogen. Of course, they're both delta positive enough to do hydrogen bonding, so they are going to both do hydrogen bonding. But the ethanol delta positive is much more delta positive, and so those hydrogen bonds will be stronger. It also probably helps that the oxygen has two lone pairs, whereas the ethylamine only has one lone pair. Okay, so that covers intermolecular forces. What we're going to do now is take those intermolecular forces and apply them to polarity and solubility concepts. And I'm going to kind of go through this set of slides pretty fast because I think it's going to be intuitive for you guys. So we were talking about overall molecular polarity, right? And now we've learned all of the different intermolecular forces that can keep things associating with each other. So now we're going to apply this to dissolving a solute in a solvent. And the rule here is really that like dissolves like. So if you have a polar solute, you want to pick a polar solvent. If you have a non-polar solute, you want to pick a non-polar solvent. And that derives from this notion that molecules that have similar intermolecular interactions among themselves will mix better with molecules that have also the same type of intermolecular forces. So let's see some cartoon pictures. Let's imagine taking a polar solute and dissolving it in a polar solvent. So let's take a big chunk of salt, which is sodium chloride, or whatever your favorite polar molecule or ionic molecule is. When we dump that chunk of salt or whatever it is into a bucket of water, then the strong dipole of water, which is pointed in the kind of downward direction, creates a situation where all these Mickey Mouse water molecules can use their negatively charged ends, so the oxygen end, to surround and stabilize a positively charged cation. And they can use their positively charged end of the Mickey Mouse, so the hydrogen end of the Mickey Mouse, to surround and solubilize the anions. And so in a polar solvent, a polar solute will dissolve. What if we take that same chunk of salt and try to put it into a non-polar solvent like, olive oil? So if we take our chunk of salt and put it in olive oil, it's not gonna dissolve, right? And the reason for that is because there's interactions happening between the positive and the negative charges of our polar solute, whether it's ionic or whether it's made up of a series of molecules with strong dipoles. Those charge differences help that molecule stay together, help that compound stay together and stabilize the charge buildup. A non-polar solvent is not able to help stabilize any charge buildup. And so the more stable scenario is to let that solid stay a solid, or whatever phase it is in, let those polar molecules or ionic molecules stick together and it won't dissolve. Okay, so here's another cartoon version of looking at a non-polar solute in a non-polar solvent. This would be something like taking, olive oil and mixing it with sunflower oil. You have these kind of non-polar molecules that are greasy, is one of the words that we call them, but they're very susceptible to induced dipoles or temporary dipoles because they don't have any dipoles of their own. There's no strongly dictating factor about where a dipole should be in this molecule. So a non-polar solvent can help to dissolve a non-polar solute because it can surround each of the molecules and participate in the van der Waals interactions with it. It is a weak interaction, but it's still a stabilizing interaction to have this non-polar solute dissolving in a non-polar solvent. And of course, we can contrast that with trying to take our olive oil and put it in water. We all know that wouldn't work. The reason is because the non-polar molecules, so our olive oil molecules, are going to be better at stabilizing each other than either they are at stabilizing the water or the water is at stabilizing them. The other thing to keep in mind here is that in this example, you can see the hydrogen bonding network of these pink dots all throughout our water molecule network. And in order to dissolve the solute would be breaking up all of those hydrogen bonds, which is typically unfavorable. Okay, so my last slide on this topic is just related to some key terms here. So I think everybody is good on the sort of kid-friendly science experiment version where we separate oil and water and have them being different colors. But you can see here that the oil molecules stick together and try to find each other and exclude out the water molecules. And this is just a real-life representation of the cartoons we saw in the last couple of slides. But it gives me a chance to talk to you guys about some keywords here: hydrophobic and hydrophilic. And these words hopefully are intuitive to you guys. Phobic is like a phobia or a fear, and hydro is water. So hydrophobic molecules have a fear of water or don't like water. So these hydrophobic molecules are going to be usually non-polar molecules, right? Because water is a polar molecule and it'll dissolve other polar molecules. On the opposite side of that, hydrophilic literally means water loving. And so hydrophilic molecules are going to tend to be polar molecules. They're going to tend to be things that, are stabilized by the strong dipole that water has and carries around with it. And so they're going to be typically polar molecules. Okay, so I have just a couple of minutes to introduce you guys to some acid-base concepts, and I'm going to go ahead and take the time to do that now. I heard from my other section that you guys have already seen some acid-base stuff. You guys have met pKa, and so some of this is going to be reviewed to you guys, but what I want to do is put it in the context of organic chemistry. And so it's going to be a little bit different way of thinking about things than what you may have been used to in general chemistry. So first of all, what do we mean when we say acid or base? And the answer to that is really there's a casual definition that's going to be used most often in organic chemistry. But one of the things that I want to point out to you guys is that we're doing exactly what I told you at the beginning of class that we would do. We're going to be using our fundamental principles of structure that we now know how to draw Lewis structures. We now know how to think about the dipoles of bonds and therefore the overall dipole of the molecule. All of that stuff is going to come into play in thinking about stability of molecules, which will relate directly to acid-base chemistry. And so we're going to use all these fundamental principles to be able to explain what we actually see for how organic molecules behave. Okay, so back to the definition. What do we mean when we say acid or base? Well, informally, the kind of rule of the road here is that an acid is something that's capable of donating a proton or giving up a proton. And this should make sense to you guys if you think about hydrochloric acid or any kind of like the famous acids. They're acids because they dissociate strongly, and so they provide a proton that can be used to protonate something else. And on the converse side, a base is something that is capable of stealing a proton or accepting or taking a proton. So those are informal definitions, but I want to take a moment to cover the formal definitions of acid-base. And there's going to be 3 types that we'll talk about in this class, but we'll focus mainly on one. And these 3 types I'll go into a little bit more detail over the next couple of slides. So this slide's just an overview. But really, these are the 3 types that were set up by some old guys who wanted to name things after themselves. So the first set is called Arrhenius acids and bases. And this is going to be compounds that dissociate to form H3O plus, or in the case of bases, OH minus. So these Arrhenius acids and bases are probably what you guys are most used to from general chemistry, because these are what connects really well with the pKa scale or the pH scale. In addition to Arrhenius base acids and bases, there's also something called Bronsted-Lowry acids and bases, often just called Bronsted acids and bases. So you'll hear me oftentimes drop the Lowry. And these acids and bases are going to be defined from the perspective of the proton. So acids are going to be proton donors and bases are going to be proton acceptors. Now you can still think about this in terms of your favorite acid or the most famous acid, HCl. HCl is going to donate a proton to some other molecule, right? So it's a Bronsted acid. It's also an Arrhenius acid because in water it will dissociate. The third kind is called Lewis acids and bases, and that's thinking about acids and bases from the perspective of an electron pair. So whether you're going to be talking about a molecule that has a space where they can accept an electron pair, or talking about a molecule that has electron pair that they can donate, that type of acid base is called Lewis acids and bases. So I'm going to take just one kind of pop-up here to remind you guys that the concepts in chapter 1 become really important here, because in order to be thinking about acid-base chemistry and what stability there is or the likelihood of something to give up a proton, we need to be able to look at a molecule and very quickly and very easily see or visualize all of the lone pairs, all of the hydrogen atoms, and all of the formal charges on that molecule, whether or not they were drawn in for us. So that's why chapter 1 and all of the work you guys did in chapter 1 to get to know that material comes in really handy again. For the purposes of this class, Bronsted acids and bases are going to be the main one that we deal with. And so I'll focus my attention on that in the last 1 minute and more so on Wednesday. But I am going to go through each of these 3 so that you're aware of them. And for Arrhenius acids and bases, then we are talking again about substances that dissociate in water to give H3O plus ions. So an example of this would be sulfuric acid in water, which dissociates strongly to give H3O plus. or acetic acid, which dissociates also in water to give H3O plus. And just for my last slide today, I'm gonna finish covering Arrhenius acids and bases and just show you the slide on Arrhenius bases. This is substances that dissociate in water, giving hydroxide ions. Again, this works on the pH scale. And here's some examples. You can see sodium hydroxide dissociating to get the hydroxide ion. And of course, more dissociation means stronger bases or stronger acids if you're talking about an acid dissociating. And then the last comment I want to make today is that this Arrhenius definition of acids and bases is not great for organic chemistry because usually we're using organic solvents and not water. And so we're going to be focusing instead on bronze acids and bases because that's the more generalized case of Arrhenius acids and bases. I'm out of time, so I'm going to stop there, but I can take a couple of questions. Okay, it sounds like nobody has any questions, so I will post these slides and I will see you guys on Wednesday.
Thank you.
Thank you.
You're welcome. Thank you guys.
Thank you.
Have a nice day. Thank you. Have a great day.
You guys too.
Thank you.